Problem 33 is asking us to find the area here defined by these three equations that they've given us, all of which are linear functions. So I'm thinking if we're drawing three lines right here, and I believe their slopes are all different, we should end up with a triangle. Let's take a look at what we've got. You'll notice all of these are in standard form, which is not totally helpful for us. So real quickly, I'll just solve each one of them for y here. We're going to get y is equal to a negative x plus 4. Here, we're going to get y is equal to x, and here we're going to get y is equal to a negative 3x plus 4. So I think I made my graph big enough to fit all three of those. Our first line has a y-intercept of 4 and a slope of negative 1. I'll actually go down 4 and right 4, and connecting those 2 points right there should give us that first line looking something like that. Second one, y equals x, passes through the origin with a slope of positive 1. At a 45-degree angle, like so. And then our final line here is y equals negative 3x plus 4. Same y-intercept of 4 here, but now we're going down 3 and right 1, which should get us to this point right over here. All right, so there's the third line. Okay, and as I thought, three lines, all of which have different slopes. And that means then, if I'm counting this right, guys, there are 7 different regions that were created here when you drew these three lines, because they're not concurrent, and only one of them is a bounded region right there with a finite area, and that would be this little triangular sliver right inside there. All of the other regions, like region 1, here's 2, here's 3, 4, 5, and 6, all of those other regions are infinite. They're not really bounded, but it's region 7 right here in the middle. That's the only one we could actually find the area of. Okay, so that's where we're at. And the first question we have to deal with on a problem like 33 here, it does not tell you whether you're supposed to integrate this region with respect to x or with respect to y, and that's a decision that we want to make early on. Now, as I'm hoping you guys have learned, both ways could be done to get you the right answer, but one of them is most likely going to be easier than the others. So, we usually like to think about vertical rectangles first. That's the way our brains kind of work, and I see a problem here. Not an insurmountable problem, but one I'd kind of like to avoid. What happens here is that that little rectangle I just drew is bordered by this line right here. That would be the first line on the top, and then this line right here, which would be the third line on the bottom. But when I go to draw another vertical rectangle, it's got the same top border, but a different bottom border. So I could do this one with respect to x, but it would require two integrals. So I'm wondering if integrating with respect to y would be easier, but unfortunately, guys, as I'm looking at that, I think I'm going to run into the same problem. There's one horizontal rectangle that is bordered on the right by this first curve right here. Y is equal to a negative x plus 4. But if I draw another horizontal rectangle, that one's bordered by a different curve or a different line on the right. So it looks like whichever way we choose to do this, we're going to have to split this region up and do it with two different integrals. So that said, I'm going to go ahead and do this region with respect to x, because that's the way most of us kind of prefer to do it. And that means I've got to split this region where the bottom border changes, which is going to be at this point right here, and we're going to go up until we hit that region there. So boy, I wish I had drawn this a little bit bigger, guys. Maybe I can kind of zoom in on that here just a little bit. And let's take a look here. We had a 4 right there and about a 4 right here. And I think I need the point 1, 1, which is maybe right about here. So if I redrew that a little bit larger here, we had a line coming down like that. We had a line coming down to this point right here. So there we go, looking something like that. And then one coming out of the origin, hitting that same point right there of 1, 1. So maybe that's a little bit easier to see. So we're looking at this region here. We're splitting the region, guys, where the bottom border is going to change, which is right here at x equals 1. So we'll call this region 1 over here and this region 2. And that's what we've got to try to work out. So for region 1, if I draw just one of those rectangles here, guys, we can see that on the top, it's bordered by the function y is equal to, that was 4 minus x. And on the bottom, which is right over here, that's bordered by y is equal to negative 3x plus 4. So for region number 1 here, guys, let's get working on this here. Area first is going to be the definite integral of top minus bottom. So that'll be 4 minus x minus, and now remember, guys, every time we subtract a polynomial, you need parentheses here. Negative 3x plus 4 provides the lower, the bottom border of that region. We're integrating with respect to x, and our limits of integration need to be the lowest and highest values of x, reading from left to right in this region. That region begins right here when x is 0, and ends right here when x is, that was 1. So that integral right there will get us the area of the first region. We're going to add to that now a second integral that's going to get us the area of region number 2. So I'll draw one little rectangle there, and let's take a look at what's going on. What stops that second rectangle on the top? Once again, the function of y equals 4 minus x. But then subtracting from that, the lower border of that rectangle right there, which was this equation right here, y equals x. So that's just going to be 4 minus x minus x. We needed parentheses here, guys, because we were subtracting a polynomial, and we have to remember to distribute that negative. We don't really have to worry about that right here since we're just subtracting a monomial. That integral is being taken with respect to x, and limits of integration, everybody. That region starts right here where the first one left off, which is still at 1, and it ends at this point right here. And I have a hunch that that's x equals 2, but I don't know that for sure. So let's find that real quick. Let me switch colors, guys, by finding the intersection of this line right here and this line right here. So that this guy right here was the function y is equal to, that was a negative x plus 4, and that equals this one, which was y equals x. Bring that x to the other side, and you're going to get 4 is equal to 2x. Yeah, divide by 2, and we're going to get x equals 2. So that is where that second region lets off. Right here, guys, is x equals 2. So that second integral goes from 1 to 2. All right, unfortunately, guys, I think, really with both integrals right here, we should probably take a moment and rewrite these in a way that might make them easier to deal with. The minus negative 3x right here becomes a plus 3x. Minus x, that's going to be a 2x. And then, we had a 4 here, and then minus 4, the 4 minus 4, they just cancel each other out, so we just end up with 2x dx from 0 to 1. And then we'll add to that another integral from 1 to 2. 4 minus x is a negative 2x plus 4 dx. So let's work on our antiderivatives now, guys. 2x, we're going to take x and square it, and then divide by the new exponent. 2 divided by 2 is just 1, so x squared is our antiderivative. We'll evaluate that from 0 to 1. Plus, this one I think I'm going to put brackets around. Antiderivative of a negative 2x is going to be a negative x squared, and of positive 4, that'll be a plus 4x. Close off the brackets there, and now we're going from 1 to 2. So let's see where we are here, guys. This is just going to be 1 squared, so that's 1 minus 0. That was pretty quick and easy. I guess I'll put brackets around that to be consistent. Plus, this one should be a little bit tougher now. The opposite of 2 squared is a negative 4, plus 4 times 2 is 8. That takes care of the 2, and then minus, let's put a 1 in there. The opposite of 1 squared is negative 1, plus 4, and that'll give us that value right there. And I think at this point, guys, we should be pretty close to finishing this whole thing off. We've got a 1 right here, plus that negative 4 plus 8 is going to be a 4. This was 3, but we're subtracting that, so minus 3. So I've got a 1 plus 4 minus 3. Looks like our answer right there is going to be 2 square units for the area of that region. And before I cheat and take a look at the solutions manual, I'd love to look at that region there and try to see if it's actually going to end up working out nicely or not. If I did a little geometry to try to guess what's going on right there, 2 square units doesn't seem crazy to me. Let's see if I can zoom in on maybe that original graph here and see if we can just come up with a guess for what that region might have looked like here. If I were to make, I don't know, like a rectangle out of all of this, this original graph wasn't perfect right here. It was 4 units tall. We've since learned that this point right here was at x equals 2, so the area of that green rectangle right there is equal to 8. So the question becomes, could that yellow area right there be a quarter of that? Could it actually be 2? I feel pretty decent about that answer, guys. So now I'm going to do what I just said I wasn't going to do, which is to go cheat and look at the solutions manual right here. I guess it's not really cheating if you did the answer already, but problem number 33, where did we go? And the answer to that one, yep, ends up being 2 units. So that, everybody, is problem number 33.